Hello everyone. In this video we're going to get started with hydraulic fracturing design. And for this case we're going to limit our analysis to a single planar fracture with a constant height. In other subsequent videos we will discuss about the variation of the hydraulic fracture height and also multiple and non-planar hydraulic fractures. First of all, why do we want to make a hydraulic fracture? In terms of completion, we want to make a hydraulic fracture in order to improve reservoir access. Basically, a hydraulic fracture is going to provide a larger surface area of the wellbore in contact with the formation. In this comparison, we have one wellbore and a wellbore with a fracture. We know that from the wellbore equation, we can compute what is going to be the flow rate out of this wellbore, which is going to depend on the permeability of the formation, the viscosity of the fluid, the height or thickness of the reservoir, the difference in pressure, the radius of the wellbore, and also the skin factor. So when we do not have a fracture, all of the fluid has to go through the surface of the wellbore. For example, if my fluid was to come into this wellbore, will have to go through the surface of the wellbore. And that surface is going to have an area which is 2 pi r h. However, when you have a fracture, you increase that surface area of the wellbore in contact with the reservoir dramatically. Here you can see from this simple geometry, considering a fracture with a constant height, that we now have this additional term, which is 4 times the height of the fracture times the fracture half length, which is going to increase this area dramatically, especially when L is significantly larger than the thickness of the reservoir. This is why we want to make a fracture, because the flow rates are going to be much higher with a fracture than without it. And you can quantify that through, for example, through these plots and computing what will be the equivalent skin factor whenever you have a fracture. I'm not going to go into details about this. This is something that you typically see in production. Here we're going to discuss specifically what are the geomechanical parameters that control hydraulic fractures. One more reason to have a hydraulic fracture would be that, for example, you want to get out of a damaged zone, a region near the wellbore that may have now a reduced permeability because infiltration of drilling mud. In order to avoid that, what you can do is you can do a fracture so that you get away from that region and you get into the area of the reservoir that hasn't been damaged by the infiltration of drilling mud. All right, so let's get started analyzing the mechanics of a hydraulic fracture. The propagation of a hydraulic or fluid-driven fracture is a coupled problem that depends on many ongoing processes or many simultaneous processes. And these simultaneous processes are here shown in this schematic, and they are 4. First, in order to keep the fracture open, you need to have a pressure on the surface of the fracture so that it remains open. We can make an abstraction of this problem and think about this as what will be the pressure needed to, for example, deform this spring that I have over here. So this is the fracture. I'm just here showing here, this will be the wellbore, and I have one wing of the fracture. The opening of this fracture is going to be proportional to the pressure in the wellbore and inversely proportional to the stiffness of the formation. We can solve that with the solutions of continuum mechanics problems. For example, we could simplify this to an elasticity problem. Second, in order for this fracture to propagate, we need to create new surfaces so that this fracture can propagate through intact rock. And that's going to depend on the resistance of the rock to fracture, and it's going to be characterized by a property called rock fracture toughness. And we're going to see how we deal with this problem with the theory of fracture mechanics. Third, as this fracture is propagating, also we're going to have Leakoff of the formation into the rock. This is going to be very important because, as you may imagine, there's going to be a gradient of pressure between the fracture and the formation, and that Leakoff is going to be proportional to that pressure gradient and also to the permeability of the formation. In order to have a propagating fracture, we need to have enough pressure in the formation so that the fracture can propagate. That means that the Leakoff will have to be reduced. So we have that gradient of pressure available. And fourth, for this fracture to propagate, we need fluid to flow through the fracture. And that flow through a fracture, sometimes we can approximate it as the flow through two parallel plates. For example, in my schematic here on the bottom, here I have the rate of fluid flow that goes through the fracture, and this is going to be a property that is also, or a variable that is also going to depend from the distance from the wellbore. All the fluid that I inject, and it's going to be characterized by the parameter I, is going to get into the fracture, and it goes into the fracture, is going to change, the pressure is going to change with length, and also the rate of the fluid flow is going to change with distance because some of this fluid is going to leak off into the formation. Let's see what are the solutions for these problems, for these four problems, and how we can solve those and put all those together into a single model. And for that, as I was telling you before, we're going to assume that this is a planar fracture and it has a constant height, which is predetermined. All right, let's get started with the width of the fracture. As we said, this is going to depend on the pressure in the formation and the stiffness of the surrounding medium. Before we get in detail about solving that width, let's get started with a definition of what net pressure is. And for that, this diagram is going to be very useful. In this diagram, I have a cross section of a fracture with a finite width. It's just so small that I'm just putting here as a line. This fracture is within a rock which is subjected to stresses, which are the far field total stresses. In this case, I have made also my schematic with my fracture to be perpendicular to the least principal stress S3. We know that this fracture would open as a plane perpendicular to that stress. For this fracture to be open, the pressure inside the fracture should be higher than the least principal total stress. That's a necessary condition for a fracture to propagate. And many times, in order to deal, instead of dealing with absolute values of pressure in the fracture, it's a lot easier to work with something which is called the net pressure. The net pressure is going to be the difference between the pressure within the fracture, the fluid pressure within the fracture, and the least principal stress. A fracture is going to open and propagate only if the net pressure is higher than 0. As I said, this is a necessary condition, but that's not the only condition that we need for a fracture to propagate. We're going to see that in a bit. But it is a necessary condition. And for example, in this case, we see that the distribution of the fluid pressure is not constant throughout the entire fracture, but it's just positive in a section of the fracture. In those conditions, we would say that the net pressure in this section is positive, and is the difference between P and S3. And because I have no pressure in these sections of the fractures close to the tips, this will be a negative net pressure. We do this subtraction because when we do that, this problem gets a lot more simplified, and we can just work with net pressures and just forget for a minute that we have far field stresses. We just assume that the far field stresses are 0, and we just work with the net pressure. Linear elasticity allows us to do that through the principle of superposition. So this problem, solving this problem, is the same as solving that problem. And that's why in these equations, we are now just working with a net pressure inside the fracture. The solution of the stresses and displacement in a line crack was solved by Griffith a long time ago. In his problem, what he did was to assume that there is a crack or a fracture which has a width. Let's start with the length. It has a half length which is C, and it has an initial finite width, but which is very small. Here I have amplified that width, but in the theory it should be quite small. On the walls of these fractures, I have a pressure, and this fracture is immersed into an infinite medium with linear elastic properties. In this case, a Young modulus E and a Poisson ratio nu. All right, so we can solve this problem, and this is the Griffith problem. And for the condition in which the pressure is uniform around the entire line crack, the solution tells us that the displacement is going to be the highest at the center. In this case, we're assuming that this fracture is just a crack which is not propagating, static. We're just solving the stresses and displacement around this crack or opening which is not propagating. And for this solution, then, as I was saying, the displacement is going to be the maximum at the center. At the tip of the fracture is going to be 0 because we're saying it's not propagating. And the solution of that displacement is given by this equation, which is the equation of an ellipse. So probably you could readily see that from this equation, if we replace x, which is the position from the center of the crack, if x is equal to 0, then we will recover what is the displacement at the center, which in this case will be 2 times the net constant pressure in this crack divided what is called the constraint modulus of the medium, and which is given by this equation, times the square root of c squared, and that means c. That would be the displacement of the wall of the crack from the center towards this point. And if we want to calculate the width of the fracture at the given pressure, then we just need to multiply this times by 2. And this is what we have over here. The width of this fracture, which is not propagating, is equal to 4 times the net pressure in the fracture, if I assume this is a constant pressure all around the fracture, times the fracture half length divided the constraint, the plane strain modulus of the formation. So I hope that you see from this equation that the width of this opening is going to be, of course, directionally proportional to pressure, but it's also proportional to the length of the fracture. The longer the fracture for the same pressure, the larger is going to be the width of such fracture. And also, as we were expecting, the stiffer the solid is, the smaller the width is going to be. With this equation, we can partially solve what we were trying to calculate in the first problem. That will be, what is the width of the fracture for a given pressure? We'll see that this is going to get a little bit more complicated later on, but at least you know that we have a solution for a simple case right now. The second equation that we're going to use is related to the stresses in the fracture. The stress, which is immediately adjacent to the fracture wall, is going to be equal to the pressure. So in this particular case, sigma yy, let me see if I can make this work. Just let me try another way of doing this. Okay, so for this example, let me complete this figure with the displacement. This is going to be the displacement in direction I, in direction y, and we now are looking at this at the stress, solving for stress. So what I was saying before is that the stress for a piece of rock immediately adjacent to the fracture wall, the stress sigma yy, the normal stress in direction y, is going to be equal to the pressure in the fracture for all the elements which are near the fracture wall. And that is going to be a compression because I'm pushing with a positive pressure, right? The question here is what happens at the tip. And at the tip of the fracture, as we're going to see later, this is going to be, instead of a compression, is going to be a tension. And that tension, that stress at that location is the stress that we're going to solve. Here in this equation, you can see that Kirsch found a solution for this stress. Let's see what happens with the equation when x is equal to c. That will be at this point. When x is equal to c, c squared minus c squared, that's going to be equal to 0, and therefore we're going to have here a wait a second. Okay, I just found a small mistake in my equation, and the right equation for sigma yy is equal to this. It is very similar to the one in the notes, but that number 1 should be outside that denominator. All right, so now what happens when the variable x is equal to c, that's at the tip of the fracture, then this is going to be equal to 0, and x or any variable divided by 0 that's not possible. That's going to tend to infinity, and that's a problem because we cannot deal with infinite quantities. And what the theory here and the solution of Kirsch actually suggests is that in my fracture, let me extend the fracture. If I were to plot this solution of sigma y as a function of length, variable x, Kirsch tells me that inside the fracture, the sigma yy is negative, it's a compression, is constant, and is equal to the net pressure. And at the fracture, this tends and goes into a tension value, which is in this case infinity. So in this case, then we're going to have the value of tension. Let's assume in this case I'm assuming that the tension is positive, that it will tend to infinity. That's something that we know that it cannot happen, and will tend towards 0 as I get further away from the fracture. Because we cannot deal with these infinite quantities, that's why we create a new definition of the state of stress at the tip of the fracture, and something what we call the stress intensity factor. And here now we get into problem number 2. Just to remind you, before we solve for what was the opening for a given pressure, now we would like to solve if the fracture is going to propagate or not. And that's going to depend on the value of stress. As I was telling you before, we cannot deal with infinite quantities for tension. That's why we create this new parameter, which is the stress intensity factor, and is defined as the limit of the product of the distance from the tip, quantified here by the variable r, times stress. So what that would mean is that when I make this product and I multiply the distance from the tip to a value close to the tip, as this gets closer to the tip, this variable r is going to get to 0. As I get closer to the tip, this stress is going to tend to infinity. But when you make this product, you can cancel those into a finite quantity, such that this limit is going to result in a finite amount. And for a constant pressure crack, the stress intensity factor results as this. It's going to be equal to the net pressure in the fracture times the square root of pi times the fracture half length c. And this is a finite value. And we use this finite value to compare it to the maximum capacity that the rock can resist. In the previous case, if we were just dealing with the stress, the Kirsch equation will tell us that the stress is going to infinity at the fracture tip. And we cannot compare that, for example, to tensile strength, because of course infinity is going to be higher than any tensile strength of the rock. So we cannot use for fracture propagation the tensile strength criterion. In order to deal with fracture propagation, when we already have a certain length of the fracture, we use this stress intensity factor. And for a given fracture with a given pressure, we will have what is the stress intensity for that fracture, and we compare that with the maximum stress intensity that the rock can support. And we measure this through what is called the fracture toughness. And this is something that we measure experimentally. So whenever the fracture intensity value is higher than this fracture toughness, then we will say the fracture propagates. whenever the stress intensity value is smaller than the fracture toughness, then the fracture will not propagate. And the fracture toughness is going to be a property of the rock that is going to be independent of the characteristic length of a given fracture. So we can use this fracture toughness for fractures of different sizes, and that still is going to work because this is going to be a property of the formation. We can measure this fracture toughness in the laboratory. Actually, we use very often a method which is called the semicircular bending test, in which we obtain a piece of rock, we cut it in cylindrical shape, and then we cut it in half, make a notch here in the center, and then put it on two rollers and apply a force on the top so that we create a tension at the tip. And the maximum force that we can apply is going to depend on the strength of the rock itself, but also on is going to be a function of this distance for this small fracture. And we can lump those two together and measure what is that fracture toughness through this equation that, as I was telling before, it depends on the maximum force that can be applied and the geometrical properties of this sample. Here I have one example of a here it is of an actual experiment with a shale sample, in which you can see here are the rollers. There is a notch here in the center, and we apply the load with the low frame, very similar to what you did, for example, with the tensile strength test. And the maximum load and the properties of the sample will allow you to compute what is the fracture toughness. And right here. So in summary then, in order to see if this fracture is going to propagate or not, we use this criterion, which is derived from linear elastic fracture mechanics, in which if the fracture intensity value is higher than fracture toughness, then the fracture will propagate. In this example, I have one problem in which we know what is the half length of a given fracture. We know what is the absolute pressure in the fracture, what is the minimum principal stress in that medium, and we know the elastic properties of the fracture. And what I ask you is that with the Kirsch equations, you compute what is the maximum width and what is the stress intensity at the tip of the fracture for this particular fracture. And if you work with the solutions, you will see this just an application of the equations that we have already seen. Notice in this case that here I have an absolute pressure of the pressure in the fracture. So in order to compute the net pressure, and before putting that into the equations of the Griffith solution, I need to compute the net pressure. Once I have the net pressure, which in this case is 0.5 MPa, I'm able to calculate this width and also the stress intensity factor, which in this case is about 2.8 MPa per square root of meter. Typical values of the fracture toughness are around 1 MPa per meter square. So let me write this down over here. Typical values of fracture toughness are in the order of 0.2 to more or less 1.5 to, we could even say a maximum of 2 MPa times square root of meter. Some shales, very strong shales, have a toughness which is closer to 2. Other less cemented rocks have a toughness closer to this value. Uncemented rocks have no fracture toughness at all. I hope that you notice here what these sort of weird units are, and notice that this is a product of a stress times the square root of length. That's why we have those units. It's sometimes very useful to me to illustrate the concept of fracture toughness and stress intensity with an example using chopsticks. And next time that you go into Chinese restaurant and you grab some bamboo chopsticks, I'll ask you to grab the chopsticks and try to break the chopstick by grabbing the chopsticks from a place very close to the tip. So I hope that you can see right now that this chopstick, you could also imagine this as a fracture problem, in which if this is the chopstick and here is the end of this part, this is going to look like something very similar to the fractures we're dealing with. And my challenge is that next time then you go and eat some Chinese food, that you try to break the chopsticks from here. Pull them from there, and you will see that it is very difficult to break them. Why? Because the stress intensity factor that you are producing at the tip of this fracture or this notch is proportional to the length between the tip and the application of the force. In this case, this would be our C. Even if you apply a large force, you'll see it's quite difficult to break them. However, usually we don't do this, right? What we naturally do is probably with the same force, we grab them from the end. Why? Because in this case, the length, let's call this one C1, this is the same force that we're applying. In this case, the length times the force, it's is a lot bigger, and so it's going to be a lot easier to break these chopsticks. And with fractures, it's going to be the same. For the same pressure in a fracture, which will be the equivalent here of our force F, the stress intensity factor and the likelihood of that fracture to propagate is going to depend on its length. The longer the fracture, the easier it's going to be for the fracture to propagate. Short fractures are usually harder to propagate because this stress intensity factor is still quite small. And let's use also this analogy of the chopsticks to discuss two other types of fracture propagation. In this case, I don't know if you know this, but we were using this parameter I or 1, and this it's because we are referring to a mode 1 fracture. And that would be a fracture in which these two faces of the fracture are getting further from each other. I hope that you remember from our previous lectures that we had three types of fracture propagation modes in solids. Mode 1, the one that we are discussing now, will be applicable for this particular problem. But sometimes also we have mode 2 and mode 3. And those two types of fractures are going to, fracture propagation might also happen in hydraulic fracturing. A fracture that propagates in mode 2, like this one, let's put it in the context of a vertical fracture. Let me change here the color. For mode 1, if I had a vertical fracture which is propagating, and if it's just pure mode 1, the new surface that will be created from propagating this fracture will remain in the same plane of the fracture. If I had mode 2, and I had an initial vertical fracture which is propagating, and now next to that tip of the fracture I have a shear stress, the new fracture is going to tend to bend according to the direction of the new added shear stress. And the new direction, in this case, and this additional stress is going to make this fracture change its direction and go according to the shear stress at the tip. And last, for mode 3, if we had a vertical fracture which is propagating in a medium and it encounters a region in which now I have this out of plane shear stress, what it will happen is that the new fracture surface would segment and form planes which are going to be in agreement or are going to follow the conditions of shear stress at the tip. Let me do that again because it doesn't look the same. They should be oriented in the same direction with the same orientation. So it's going to look something like this. And here I'm just drawing two, but we could have more of these segments that would happen at the tip of the fracture. All right, so this is just for your information. We're going to revisit some of these influence of mode 3 propagation when we talk about non-planar hydraulic fractures. But for now, the discussion that we did is enough. I wanted to mention this because associated with these new types or these other types of fracture propagation, also we're going to have the K2C and the K3C, and those will be the fracture toughnesses associated also with shear. Okay, so so far we have solved two of our main problems in hydraulic fracturing propagation. One was we were wondering what would be the width of the fracture as the fracture propagates. The second question that we had was if the fracture would propagate or not, and we answered that through the fracture toughness of the rock. And the two more that we're going to have to solve are going to be related to the Leakoff and to the pressure gradient in the fracture. All right, so for the Leakoff, it's a relatively easy problem to solve. We just need to do a mass balance. We know that the total injected volume into the formation is going to be is going to divide into the volume that actually stays in the fracture plus the volumes that leaks off into the formation. In order to compute what is the volume of the leak-off, we have two options. We could use some simplified equations like the Carter equation that utilizes the area of the fracture and the Carter leak-off coefficient in order to tell what is going to be the leak-off coefficient as a function of time. I hope you remember from previous discussions that we said that whenever we have a fluid flow around the fracture, those processes are going to depend with the square root of the time. So this is why we have this parameter in here. This will be the time since the beginning of the leak-off. And we can also quantify that amount of leak-off with this efficiency parameter eta that characterizes what is the volume that stays in the fracture compared to the total volume that we injected. In general, if we want a fracture to go long and to have a high efficiency of our hydraulic fracture in filling the fracture, we would attempt to have this parameter that goes close to 1. Because if this parameter goes to 0, that means that all the fluid that we inject is going into the formation pore space rather than into the fracture. We can make a simplification also to compute what is this injected volume. If we have a constant injection rate I, and then the injected volume is just going to be equal to the constant injection rate times the time. So that's going to be a very easy number to compute. For these computations, it's very important that you remember that this injection rate I is considered just for one wing of the fracture. So if you want to compute what is the total amount which is injected at the wellhead, you need to multiply this times 2, because you would have most times 2 wings instead of just 1 wing in a fracture. All right, this is the problem of the Leakoff. And the last problem to solve, it's a transport problem in which we want to know what is the pressure gradient as we move in the direction of the fracture from the wellbore to the tip. For that fluid flow to move in the fracture and to go from the well to the tip, let me redraw that over here. This is going to be, if this is the wellbore and this is our fracture, then we're going to have, as a fracture propagate, a fluid that we were saying that moves from the well through the fracture. And let's forget a minute now about the Leakoff. This flow rate is going to depend on the width also of the fracture. For two parallel planes, the solution of this flow rate is given by this equation. We can use also in fractures this equation, but we just have to take into account that the width is going to vary with the distance from the wellbore through the tip. And we saw before how to calculate that width, so we know that part of the problem. The other part of the problem is to know what is a fracture height, something that we will take for granted in this discussion and we explore a little bit further on. We know also what is the pressure. Right here we will have the pressure in the wellbore is going to be a given pressure, and usually at the tip of the fracture we assume that the fracture is equal to 0. The net pressure at the tip of the fracture is equal to 0. So we have a delta P, we have the width, if we have the viscosity of the fluid, and we have the height of the formation, then we have everything we need in order to solve this problem. So if we put all of these equations together, we're going to be able to solve this coupled problem of a fracture propagation. And actually this is everything that goes into most hydraulic fracture simulators. Let's see some solutions which are analytical solutions for single planar models with constant fracture height. These are called the PKN, KGD, and radial solutions that will tell us what is the fracture length, the fracture width, and the pressure at the wellbore as a function of time. And for these three solutions, what they do is they assume three different shapes. And these shapes in the PKN solution, I'm going to go in detail now about talking about each of these, is going to assume that we have a constant fracture height and that the cross section of a fracture is given by an ellipse with a shape which is given by a constant pressure at a given distance from the wellbore. So this problem that you see over here, now in these semi 3D dimensions, we solve what is the width at every point along the fracture, and you see that it varies with depth with this equation. And solving that and solving for the amount of flow that goes into the fracture as a function of distance from the wellbore, you see this width is going to vary with distance. We can tell what is going to be the evolution of the fracture length, what is going to be the fracture width, and what is going to be the pressure of the fracture for a given injection rate. And as I was telling you, you just have to put all the equations that we saw before into this problem, and you will be able to obtain these equations that will allow us to predict what is a fracture half length as a function of time for a constant injection rate, the width of the fracture as a function of time, and also the net pressure at the wellbore as a function of time. And as you can see, these fracture lengths, fracture widths, and net pressures are going to depend on injection rate, the stiffness of the rock, the viscosity of the fluid, and what is the fracture height. And they are scaled according to different powers that depends on which of these equations you are taking. But in general, what these equations predict is that the fracture half length is going to increase to the power of 4/5 with time. But what that means that, and it makes sense that as if time is positive, the fracture length is going to increase. The equations also predict that the width is going to increase with time to the power of 1/5. And these equations also predict that the net pressure is going to increase with the power of 1/5. And you will see that this is something that might be different in the other models. But I just wanted to highlight that. And something very important to take into account is that this PKN model, it's used usually for long fractures when the fracture half length XF is larger than the fracture height, and that's usually the case for completions when we desire to have long fractures. And in this case, this simple solution also, in order to arrive to it, we assume that there is no Leakoff and that the net pressure at the tip, as we were saying before, is equal to 0. Assuming all of these hypotheses, you can arrive to this equation. And something very important also from this solution is that you can compute, according to the shape of this fracture, what is the volume of the fracture. And the volume of the fracture is going to be given by this equation, in which you can calculate based on the width and the height and the length of the fracture what is the volume. This is something which is going to be very important because it will allow you to design what is the amount of fracturing fluid that you need. What is the amount also, if you know what is the mixing ratio with propant, what is the amount of propant that you might also need. Just for you to work a little bit and to play with this PKN model, here I have put an example in which we have a constant injection into a formation with this plane strain modulus, with a viscosity which is close to the viscosity of water, a given injection rate, a given fracture height, and what I ask is that you compute what is the fracture half length, the width of the fracture, and the net pressure as a function of time. And using the equations that we saw, you can calculate that straightforwardly out of these equations just by replacing all the variables in here. Something very important in order for you to be able to solve these problems is that you, at least that's what I do, that you convert all your variables to the international system. That's going to make it a lot easier in order to avoid confusing unit conversion. Notice that here we have several variables which are elevated to different powers. If you try to do the unit conversion for all of that, it's going to be a real nightmare. So I suggest that you pass everything to international system units, and after that you're going to get your answer in international system units, and then you convert that back to whatever units you want. All right. And if I was saying before, if you knew what is the mixing ratios for your fracturing fluid, out of this you can compute right away what would be, for example, the amount of water needed for this treatment, or what would be the amount of propant also needed for this particular treatment. Notice that for this particular solution, we need about 2 medium-sized swimming pools in order to fill the volume of this fracture, and also we need about 6 big trucks of propant in order to fill up this entire fracture. Another model available for solving this simple planar hydraulic fracture is the KGD model. In the KGD model, the assumption of the fracture shape is a little bit differently. Here we assume that the width is constant along the entire fracture height, and we solve for stresses and width of the fracture, assuming a cross section which is in a horizontal plane if we had a vertical fracture. And we can do something very similar to what we do for the PKN solution, and also we can arrive to similar equations as the ones that we arrived before. And this is going to be a different solution, and it applies mostly for fractures which are relatively short, in which the fracture half length is lower than the fracture height. This should be the case, for example, of short fractures that happen when you're drilling, or short fractures that you are doing for just getting a little bit out of the wellbore in a damaged zone. For example, this is applied also for sometimes for frac pack completions, in which the fractures are not necessarily meant to go long into the formation, but they are meant just to be short and just to bypass the near wellbore region. And in this case, something interesting is that, of course, your fracture length and the width, they increase with time, but according to this KGD solution, the net pressure decreases with time, which is something that is observed mostly right after you overcome the breakdown pressure, but usually this is not the case in real applications, that the net pressure is going to decrease with time. And there is also the solution of the radial case, something that we are not going to see, but you might find that solution either in this paper that I'm pointing to the reference to right here, or also in the book of fracture mechanics by Valco and Economidis. You'll find those solutions there. The point of this lecture and the point of this discussion is to explain what are all the fundamental processes that go into hydraulic fracture propagation, and how you can treat those mathematically and with physical models. When you put all of those together, and if you assume a simple geometry like PKN, KHD, or radial, you can arrive to these analytical solutions that we have shown. These analytical solutions have been used for a long time, and they are more or less good for just a single fracture out of a single wellbore, but they are not that good for the current hydraulic fracture completions that we do today. But the physics is still the same. And we are going to see in an extension of these models that in our next discussion, we're going to include the variability of the fracture height with pressure and with depth as well. And we'll see how these models and that physics extends whenever we have these variable heights or variable conditions of stress. And by putting all of these together, it's going to be very difficult to solve that analytically, but that's where the hydraulic fractures simulator, they get into the picture, and that's what we use to solve these equations numerically. But for now, these lectures, again, limits to the basics, and that's what I expect that you learn out of this video.